Hello everyone. Today I'm going to present the paper Order the Faces by Diffusion Map, ISO map, and local linearly embedding. My major is bioengineering. First, you can see I chose this topic, the topic 4, from the Project2, Order the Faces by Diffusion Map. The dataset contains 33 faces of the same person in different angles. You can see the faces here. Here. These are the 33 faces in the right order. Okay, let me introduce you my paper. In this paper, I used some manifold learning methods to reduce the dimension of the 33 high-dimensional face images. I use the diffusion map, MDS ISO map, and the local linearly embedding to find the low-dimensional embedding of the face images. By comparing the scatter plots of the low-dimensional embedding and the face order graphs, we found the diffusion map, ISO map, and the LLE can get correct low-dimensional embedding results, while MDS performs poorly in this problem. In addition, we compare the MDS with ISO map, and also we compare the ISO map with LLE respectively. First, an assumption that if we want to use the manifold learning to reduce the high-dimensional data, an assumption is that the data needs to concentrate around a low-dimensional manifold. In this paper, the data set contains 33 faces of the same person in different angles, so it can meet the basic assumption for manifold learning. The data set we use contains 33 faces of the same person in different angles. This is the link. I can give you a brief introduction to the methodology, the diffusion map, ISO map, and the local linearly embedding. You can see ISO map is an extension of multi-dimensional scaling, where pairwise Euclidean distance between the data points are replaced by geodesic distance computed by graph shortest path distance. The algorithm, and you can also see the local linear embedding. The algorithm assumes that any data point in high-dimensional ambient space can be a linear combination of data points in its neighborhood. I implement all the method in Python and got the following results. You can see manifold learning with 33 points. That means 33 face images with k equals to 5 neighborhoods. This is the result of the diffusion map, and this is the MDS ISO map and the local linear embedding. These are the projections on the two eigenvectors of 4 methods. Now let's look at the diffusion map. This is the diffusion map projected on 2 eigenvectors. After ordering the face on the first eigenvector, we get the following faces order. You can see from left to right. The faces it can successfully show the gradually changed angles of the captured faces. Now let's look at the MDS. This is the result of MDS. After ordering the phase on the first eigenvector, we get the following phase order. You can see it seems to be right. However, one big problem of MDS is that it's not stable. If we repeat the calculation, we got the following two scatter plots. You can see every calculation. After every calculation, the result is different, and we got another phase orders. You can see there are several phase images are in the wrong position. You can see this image, and in this calculation, the order is also not correct. So that means MDS performs poorly in nonlinear dimensionality reduction because it uses Euclidean distance to calculate the porous distance or similarity. Now let's look at the isomap embedding. The isomap is implemented in Python on the k=5 nearest neighbor graph. And after ordering the phase on the first eigenvector, we can get the following phase order. You can see the result is correct. We make a comparison with MDS. You can see the first two graphs is the result, is the scatter plots of MDS, and the third one is the isomap. You can see these two are the phase orders calculated by the MDS, and this one is the result of isomap. By using the isomap, we can get the correct phase order. Why? And what's the reason? Because isomap use the geodesic distance to measure the distances between the points, so isomap can get correct results. Also, we do LLE embedding. These are the results of LLE, and you can see that LLE can also get correct phase order. We make a comparison with isomap. This is the result scatter plots of isomap, and this is the scatter plot of LLE. You can see the scatter plot of LLE is smoother than isomap because LLE spans nearly also because LLE stitches the graph by finding a set of ways that performs local linear interpolations that closely approximate the data, while isomap does this by doing a graph transversal. From this graph, we can also see that the LLE spans nearly twice the time of isomap, which means it needs more calculation time. So in this paper, we correctly ordered the phase by diffusion map, isomap, and the LLE. And the results of MDS shows that it performs poor in manifold learning, but its extension isomap can get correct phase order. Compared with isomap, LLE can get smoother scatter plots, but with more computational time. The two-dimensional scatter plots of diffusion map and LLE looks to be similar. Let's look at the Python code here. This is the original Python code I wrote for the calculation. Now we execute it. You can see we get the following result and the calculation time of 4 methods and the graph I showed in the paper. Okay, that's all. Thank you.